Okay. You've got your notes, and there's a whole bunch of fluff here. The first 6 slides we can sum up like this. Avogadro comes up again. Yay! Gay-Lussac comes up again. Yay! They both did a lot of work with gases, surprisingly enough. Grab your periodic table and pull it out for a second. So hopefully you've got the diatomics marked. Find them. Or you just know the diatomics if you're using the periodic table out of your agenda. Okay, what do all the diatomics have in common? Ding, 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 ding. Ding, 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 ding. Ding, 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 ding. Ding, 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 ding. Okay. Whoops, I always want to do that. F2, Cl2, 1, 2, 3, 4, 5. Br2, 6. What am I missing? Yeah, okay. And they're halogen. Yeah, they're all gases at room temperature. So basically, the work that Avogadro did with gases and gas volumes led to a better understanding and more substantial sort of rationale for why these diatomics exist and the fact that they do exist. That's pretty much what we're going to say about the first 6 slides. So here is the other cool part, and this is where we come back to Avogadro. So let me go to your what do you... So we said we have some quantity of gas, and the pressure is constant and the temperature is constant, yet the volume increases. And a few of you said, well, then you must have added more gas to it. Yeah, exactly. It's really pretty intuitive that if the temperature and pressure are kept constant, and yet the volume changes, you had to add more molecules of gas. And this is actually, I mean, it's so, you would think, well, yeah, you know, a bright 6-year-old could come up with that if you offered them a cookie. But it wasn't necessarily so obvious. And this is actually Avogadro. This is back to Avogadro. And what he came up with was the idea that gas volume is directly proportional to the amount of the gas. So expressed algebraically, that means that volume is the product of some constant and the number of moles. N is number of moles. Okay. So when volume goes up, number of moles has to go up. If number of moles goes up, volume has to go up. If you take out some amount of gas, the volume is going to decrease. Pretty stinking simple. And remember, Avogadro had, I won't call it a fascination, but he had worked a lot with the idea of counting units of chemicals. So though he did not come up with Avogadro's number, it comes out of his work. Which, you know, let's think about Avogadro's number for a second. Let's take a moment to reflect and appreciate. That we have this wild number. I mean, I would not come up with this number randomly if you said, pick a number. It wouldn't be that. And yet it's almost got this magical property that if we take this many of a group of atoms, the mass of that many of them is the same as the atomic mass in grams. That seems sort of mystical and cosmically weird to me. If you really spend some time thinking about it, you know, so drink too much coffee and stay up until about 4 in the morning and contemplate that one some night. Let your brain turn inside out on that. So we have this sort of magical mole. Well, that's fascinating, Moser, but what does it have to do with gas stuff? Would you believe me if I told you that 1 mole of O2, which remember is that many things, 6.022 times 10 to the 23rd molecules of O2, at standard temperature and pressure, has a known and predictable volume. Okay, that's not crazy, right? And it's 22.4 liters. Okay, I can accept that. And O2's got a mass of, what, 32 grams per mole, so relatively heavy gas. Well, what if I told you that one mole of hydrogen at STP had a known and predictable volume of 22.4 liters? Does that seem wrong to you? I mean, oxygen's fairly massive, 32 grams per mole. Hydrogen is the lightest stuff we've got. H2 is 2.02 grams per mole. How could they occupy the same volume under the same conditions? That just seems wrong. But it's not. And this is called molar gas volume. Can I do this without falling off the stool? Yes. And this box has a volume of 22.4 liters. Okay? So 1 mole of any gas, whether it's monoatomic or diatomic, one of the noble gases, O2, hydrogen, whatever, at STP is going to take up this much space. Okay. Well, that's handy. It's handy because we can use it as a conversion factor. And it's possible because the volume of gases, don't forget, thinking about kinetic molecular theory, most of the volume that gases take up is really empty space. So it doesn't have so much to do with their actual mass as the space between them. And that's really governed more by conditions of temperature and volume. So, as their temperature and volume changes, so does the amount of space between those molecules. They just keep spreading out. So at STP, any gas you can name has a volume of 22.4 liters. Fantastic, because we can use this, and it's called molar gas volume. We can use this as a conversion factor now. So if you would be so kind as to go to page 336 and 337 in your book, we'll do a couple practice problems together. Okay, so at the bottom of 336, we've got practice problem 1, and it says, at STP, what is the volume of 7.08 moles of nitrogen gas? So this is a simple factor label because it's at STP, so we start with our given, 7.08 moles of N2. And what I tend to do for myself is I will write here at STP, because you can only do this if you're at STP. So if you try to do this with something that's not at STP, you're not going to get the right answer. And once I've got that, I can go ahead and say, oh, well, 1 mole of N2 at STP has got a volume of 22.4 liters of N2. Okay, who's got a raw number? 158.592 liters of N2. And how many sig figs do we have? 3. So this would be 159 liters of N2. These are nice. These are easy. And of course, because we're in moles, we can also get mass. So let's look at 1 in reverse, which is number 2 at the top of 337. A sample of hydrogen gas occupies 14.1 liters at STP. How many moles of the gas are present? Well, 14.1 liters. I'm going to make my little note to myself at STP, and this is hydrogen. And I know that at STP, 22.4 liters of hydrogen is equal to 1 mole of hydrogen. So who's got a raw number for me? Okay, so we get 0.62944, etc., etc. Moles of hydrogen, we have 3 sig figs, so this becomes 0.629 moles of H2. This is a pretty awesome conversion factor. Okay, let's do one more that incorporates mass, and then I'll turn you loose to work on your own. So if you look down at the bottom of 337, the second set of practice problems, number 1. What is the mass of 1.33 times 10 to the 4th milliliters of oxygen gas at STP? Aha! We have to do something else. So 1.33 times 10 to the 4th milliliters, which means we have to convert to liters. And we can do this all as one factor label. So 10 to the 3rd milliliters is 1 liter. And we know that 22, and this is at STP, I'm going to write my note to myself, 22.4 liters, whoops, and I forgot to put in my O2, of O2 equals 1 mole of O2. So now I'm ready to get a raw number. Jeez Louise, I'm not ready to get a raw number. What were they asking for? They're asking for the mass of this amount of O2. So I have to go one more step. 1 mole of O2 has a mass of what? 32 grams. 32.00 grams of O2. Now we're ready for a raw number. Who's got a raw number for me? You get 19 even. Now how do you make that into 3 sig figs? 0.0. So yeah, 19.0 grams of O2. Okay, pretty simple, pretty straightforward. You have practice problems. They're on the board. In the chapter review, numbers 12 through 15, only do parts A and C. That'll get you plenty of practice. And then you'll have a FIP quiz on Monday. So that's your first math concept from this chapter. That's it.